Good morning. I'm going to be talking about syntax, about why we love syntax in our programming languages, why we probably shouldn't, and how you can get it anyway and take advantage of it. The motivation for this talk is the new role that JavaScript has suddenly unexpectedly found itself in. JavaScript is now the universal virtual machine. Languages are being translated into JavaScript in order to allow them to run everywhere. One of the first languages to do that was Java. Google translates Java into JavaScript so it can run everywhere. Amazing. People are now translating C into JavaScript and running at near native speeds. Nobody ever thought JavaScript would be used this way. We're also seeing new languages being developed specifically to translate into JavaScript. So it's become a universal virtual machine. I would contend the first language designed to run as one of these JavaScript languages was JSLint. JSLint could be thought of as a compiler for a language called the good parts. And so it was the first. It was released in about 2000. And as you know, JSLint comes with a warning. JSLint will hurt your feelings because it complains about people's syntax. And people have a deep emotional connection to their syntax. So when you tell them how they can improve their programs in order to make them less likely to be buggy and more maintainable, more readable, and all of that, they start to cry. Which is surprising because it's just syntax. Why should anybody care about that? So I contend that syntax is the least important aspect of a programming language design. And I mean that in the same sense as fashion is the least important aspect of clothing design, which sounds like a radical statement. But if you look at what clothing is and what it should do, it should protect us from the sun and from the cold and from injury and protect our modesty. But that's not what we consider when we buy clothes. In particular, in things like shoes, people will buy shoes without asking, can I walk in them? Can I run in them? Will they save my foot from injury? People will buy shoes that are likely to cause injury in the name of fashion. So we forget what's really important. And as programmers, we think we're smarter than that, that we would not, if you look at the completely unfashionable shoes that we're all wearing, we would not make that mistake. But when it comes to programming language syntax, we make exactly the same mistakes for the same reasons. We're totally irrational and emotional in our love for syntax. So I'll offer as evidence an amazing book by Samuel Kamen, came out in 1990, so it's a bit dated, but it's still a really good book, Programming Languages, an Interpreter-Based Approach. In this book, he writes interpreters for 7 programming languages. And then he writes programs for each of those languages to show how they work. And for these 7 languages, he doesn't implement the entire language because that would be too much work to do in a book. So he only implements the good parts of each of these languages. And for most of the languages, that does not include their syntax. So it's really surprising when you look at a language like APL, which is famous for the way it looks. It looks radically unlike any other language. He writes it with the same notation as the other 6 languages in order to get an apples-to-apples comparison. So it's surprising that you can write in a language without using its syntax. But usually when we're reviewing languages, syntax is all we look at. We look at the most superficial aspect of it, and often it could be years before we discover what's in the deeper layers. By stripping away all of the syntax, Kamen shows us what these languages are actually doing. So the language he uses is a minimal syntax. And there are a number of languages which have fairly minimal syntaxes. These languages are well regarded by designers, but are rejected by the mainstream. Most professional programmers can't stand these languages. So Lisp has a minimal syntax. It has S expressions. An S expression is just a sequence of symbols wrapped in parentheses. Usually they represent function invocations and expressions, but they could contain data or any other kind of structure. And it's really simple. You can take any of those arguments, replace it with another S expression, and nest as deep as you want. This is maybe the most minimal syntax. The Lisp community and scheming community love this stuff. The rest of us hate this stuff. We find it offensive to even look at it. Small talk could be considered a minimal syntax, although it's significantly more complicated than S expressions. The method invocation in small talk is brilliant. You have something representing an object, then you have the name of the parameters separating the values of the parameters. We rejected this, even though it's brilliant. Instead, we took C++'s approach, which is you have a list of things wrapped in parentheses, separated by commas, with absolutely no indication as to what they are and what order they go in, which makes it much easier to substitute the wrong value or to get them out of order, and we like that. We like that it's easier to get it wrong. So that we rejected this one, which is much harder to get wrong, in favor of the one that's much easier to get wrong. That's a sort of emotionalism that's wrapped up in our appreciation of syntax. So let me take you through the years and look at the evolution of the if statement. We start with Fortran. Here we have a Fortran computed GOTO statement. So if the difference between A and B is negative or 0, we'll jump to statement 20, which does nothing. Otherwise, we'll jump to statement 10. The parentheses around the condition are absolutely necessary. In most languages, they're just decoration. But in Fortran, spaces were not significant. So it could not see the difference between if A and if a. They both look the same to Fortran. So it needed the parentheses to separate so it could tell what was an if statement. Fortran gets a little better with Fortran 4. The less sign hadn't been invented yet, but it could substitute a dot, LE dot expression. You can see what it does. We can also see here the GOTO statement demonstrated. The GOTO, of course, was the inspiration for this conference. And most people wrote GOTO as 2 words, even though it's a single word in Fortran. Again, because of this ability to insert spaces anywhere. Spaces aren't significant. So Fortran actually got something right that everybody's gotten wrong since then, which is how do you write a variable name which contains a space? So we're all arguing, and we've been arguing for years, should we use underbars or camel case? And it's hard to get consensus because both are the wrong answer. Fortran actually got it right, but we haven't figured out how to do that unambiguously in future languages. So maybe someday we'll figure that out and we'll be able to use spaces appropriately. This is Algol 60, maybe the best design by committee in the history of programming languages. Algol 60 gave us the block statement. So you see the begin and end. And that introduces a scope if you're declaring variables there. And we've seen that brilliant idea carried into virtually all languages today. Algol also gave us the semicolon. There were earlier languages that tried to use periods to end a statement, because that's how we end statements in our writing. But that turned out to be problematic because it looks like a decimal point, and sometimes it wasn't clear, is that the end of a statement or is it just a number? So we went to semicolons instead. And we've seen that convention copied into a lot of other languages. This is BCPL. BCPL is the good parts of a much larger language called CPL. CPL, like Ada and PL1, was intended to be one of those universal languages which could be used for everything. That turns out to generally not be a good idea. That smaller specialized languages are usually better. And BCPL was a very successful language. And was highly influential in at least 2 ways. The first was that it came with a virtual machine that used bytecodes that was written in BCPL. So that virtual machine was very easily ported to other machines, and so BCPL showed up in lots of places. And that bytecode architecture found its way into the Pascal P system and then into the Java JVM. But it was also very influential in its syntax. BCPL was the first curly brace language. And the curly brace thing has taken off, and we see it virtually everywhere now. It's basically the same idea that we had in Algol, except instead of begin and end, it's curly brace. And we really liked that. We really liked that economy. This is the B language. This was Ken Thompson's reinterpretation of BCPL. His idea of the good parts. He tried to make BCPL a little bit smaller and to make the syntax better suited to Ken Thompson. One of the things he did was, in my view, a regression. He put the parentheses back in. In this case, the parentheses are not needed. They're here solely for decoration. And it's something that's hearkening back to Fortran. They're not needed here, but he wanted them. And so they went into B, and they went into C, into C++, into Java, into C#, and virtually every language since then has these unnecessary parentheses in it. And we think they look sharp. They serve no purpose at all. And I often find people doing stupid things in order to avoid keystrokes, but they like these keystrokes. And there's no explanation for why that is. This is Ada. One of the things I like about Ada is the way it says comments. I think the dash thing to introduce a comment is just really nice looking. Of all the comment conventions, it seems to conform most closely to what we do. And it's also using the annotated end. So instead of Algol, which would just say end, it says end if, which is a little verbose, but it's clear as to what's going on here. I think the best if statement I've ever seen is in Algol 68. This was another attempt to make a huge universal language, and there's a lot of stuff in Algol that I don't like, including its comment convention, using a cent sign to both end and begin comments. Starting and ending comments with the same character is asking for trouble. The line, or comment to the end of the line convention seems to work a lot better. But I love its if statement. It replaces the end if with phi. So you very quickly learn that that two-character digraph closes the other thing. We got rid of the blocks. It's just so elegant. I love this. I think it's very nice. Also, it's using colon equal. There's been a battle in syntax design for a long time as to, is assignment equal or is it colon equal? In Fortran, it was equal, but equal looks like equality, which it isn't, and that's confusing, and particularly the mathematicians have trouble with that. Some languages like Algol started the convention of colon equal, and we still have this argument going on. And right now, the equal sign guys are winning, and I think that's unfortunate too. So what we really like is emotional style. We could have minimal syntax, but we don't. We want the emotional syntax instead. And in particular, what we're looking for is fashionable tolerance of some syntactic ambiguity. Ambiguity is bad in programming languages because ambiguity causes confusion, confusion causes errors, and we want zero errors in our programs. But we love syntax, which makes it more likely, and in fact enables errors to occur, which couldn't occur otherwise. So I'll give you an example. So here we have a made-up programming language with two operators, cloud and heart. And I've got three variables, A, B, and C. And so how do you interpret the expression A cloud, B heart, C? There are a number of ways you could do it. One is you could read it from left to right. So you do A cloud, B, and then you do heart, C. Or you could read it from right to left. And so that would be BC cloud, and then BC heart, then you cloud that with A. There are languages which do strictly left to right, like Smalltalk did that. And there are languages that go strictly right to left. APL did that. Which is right? I don't know. But you pick a direction and you say that's how we do it. And that makes it pretty easy to read programs written in those languages. You just have to know the rule. And once you know that rule, one rule, it's that way or that way, then you can correctly read programs. But that's not what we want because that's not complicated enough and that doesn't produce enough opportunities to make mistakes. So what we instead want is operator precedence, where we want a rule which is more complicated, which describes which one you do first. And so depending on what the relative precedence is between cloud and heart, that will finally determine how that expression gets interpreted. So the way we deal with that is with binding powers. We can give each operator a number, and operators which are associated with a higher binding power bind more tightly or bind first, and operators with looser binding powers will bind more loosely and later. So basically, if you're working in a language, you have to memorize this list. You have to know the relative rankings of all of these. And that can be a difficult thing to remember. So for example, at power 40, I've got logical and logical or. And in this language that I'm going to create here, they have the same precedence. But in a lot of other languages, they don't. One of them will bind more tightly than the other. So I will ask a question to you right now. For your favorite programming language, which binds more tightly? And, or do they have the same precedence? So who knows for sure how their language works? I'm seeing a very small number of hands go up. So what that means is if your hand didn't go up, if you ever see both of these operators in the same expression, it's likely you're going to misunderstand what it does. And if you did raise your hand, and if you put both of these into an expression, it's very likely the next person to read your code will not understand what your code does and introduce an error. And it amazes me that most of the people writing programs professionally won't know the answer to that. And there's really no reason to expect that they would. Another example on line 60. In mathematical notation, multiplication is generally tighter than division. So we can write things like ax over by. In some programming languages, that's also true. But in some programming languages, they have the same precedence, as I showed here. So again, who knows for certain in their favorite programming language whether multiplication and division have the same precedence? Again, a few hands go up, but most of the hands don't, because most of us don't know. So we like that. We like that we put rules into our languages which most of us don't know, which are opportunities for creating bugs. Another source of ambiguity that we like is the overloading of words. So we can use a word to indicate a variable, a statement keyword, an operator, or a special form. And sometimes it's really important what a word is. And in some languages, there will be lists of reserved words that cannot be used for other purposes because they may conflict with some of these special uses. And most people working in those languages do not have a fully memorized recollection of what that list is. So that's also introducing other opportunities for making errors. We have overloading of operators. So in most of our languages, we'll use parentheses to do function definition and invocation. We'll also use them to do grouping within expressions, and we'll also use them for separation and decoration. So using the same operator to do all of those things can often also introduce ambiguities, which can cause errors. But we like overloading. In fact, we like it so much that some of our languages specifically allow us to do overloading, which increases our ability to create confusion within the programs that we develop. So the way we deal with ambiguity in language is parsing. And we have wonderful formal theories of formal languages which allow us to automatically generate parsers. Parsing is a very complicated subject. There are a lot of amazing books and a lot of papers about it. A lot of machinery has been constructed around it. So I'm going to write for you today a parser of a language. Now, we're going to see the whole thing. So we're going to start with tokens. You can take all of the source elements of a program and divide them into tokens, and each of those will be represented by an object. We'll have a prototype token, which will be the token that everything is going to inherit from. And then we'll have a set of symbols which will inherit from those prototypes. And then we'll have the final tokens which will inherit from those symbols. We'll have an advanced method which will fetch the next token for us and put it in a variable called token. And if we pass an ID, then it will guarantee that the token that we're skipping over is that kind of a token. So if we're looking for a plus sign, we can say advanced plus, and that'll guarantee that the next token is a plus sign. If it's not, it'll produce an error. So in parsing, what we want to do is to take a tree, or to produce a tree. So we'll take a list of tokens, and we'll weave them into a structure. And once we have the structure, we can then pass it to an analyzer or to a code generator or an interpreter, and it'll cause work to happen. So the whole effort of parsing is to produce this structure. I'm going to show you a technique called top-down operator precedence. This was invented by Von Pratt when he was at MIT. He's teaching at Stanford now. He presented it at the Popple conference in '73. He designed it for providing Lisp or high-level language syntax into a Lisp environment. He claimed that the technique was simple to understand, trivial to implement, easy to use, extremely efficient, very flexible, and I will also claim that it is beautiful. I think this is one of the most beautiful, elegant things I've ever seen. So why have you never heard of this? If it's such a good thing, why is this completely unknown to you? Pratt, in his paper, tells you why it's going to be rejected. First is the preoccupation with BNF grammars and their various offsprings. Pratt loved automata theory and all of that stuff, but he found a way to completely avoid that stuff and much more quickly solve the problem. It requires a functional programming language. And in his paper, he used Lisp. And the problem with that is that most languages, at least at that time, were not functional programming languages. And the Lisp community had no use for syntax. They had found so much value in the minimal syntax of S expressions, they didn't want anything else, even if it came at very low cost. But the JavaScript community is a community that has a functional language, and it's a community that likes emotional syntax. So this algorithm is really well suited to that community. So Pratt takes parsing, which is a really complicated thing, and reduces it to one simple question. What do we expect to see to the left of a token? There are some things that don't look, that want to see something to the left. For example, an infix operator will take something that's to its left and then something to its right. And then there are things like variables and constants and unary operators that don't expect to see anything to the left. So just those two cases. And so he calls something that is expecting to see something on the left a left denotation or a led, and something that doesn't, he calls a null denotation or a nud. So led and nud are Pratt's terms, but I'm going to use those. So there are some symbols which will have only nuds. So exclamation point in JavaScript or tilde in JavaScript, those are unary operators only, so they will have nuds. Variables will have nuds. Then plus, dot, assignment operators, relational operators, those are leds because they expect to see something on the left side of the operator. And they're to make things maximally confusing, we have some which have both. So plus in JavaScript is both an infix operator and a prefix operator. Paren is both, when it's grouping, is a prefix operator. When it's invoking, it's an infix operator. So here is the prototype token. This is where our tokens are going to start. It will have the default nud and led functions, which will just cause errors. If you get to this and these methods haven't been overridden, then the default is to produce an error. It'll also have an error method, which will produce error messages. So if we find an error as we're parsing, we can call the error method of the particular token that caused the error, and that will give us a proper message. And it will also have the default left binding power. So this is the precedence of this thing. So something which doesn't already have a specific power will inherit to 0. Then we'll produce our symbol table. That's where we'll keep all of the symbols of the language. And we'll have a symbol function which will help us to populate that table. So the symbol function will take an ID and a binding power. We'll look up the current symbol in the symbol table, and if we find it, then we'll use it. Otherwise, we will construct a new one and stick it into the table. Having this, we can now start declaring our language. So I'm going to specify that all of these things are symbols now. And it's starting to look declarative. Even though this is all procedural, this is all functional, it starts to look like declarations. So I'm declaring that these specific things are symbols. And I'm adding 2 special symbols here. End represents the end of the program. So I want something to indicate when we get there. And because of the rules of tokens, of tokenization, these are guaranteed to not match anything that actually gets read in. And then I also have a special symbol which represents words that we don't have in the symbol table. This is going to be where our variables show up. So now let's start defining operators. So plus is a symbol. It's going to have a binding power of 60, and it will have a lead, and its lead will take its first member as whatever was on the left, and then call the expression function to get whatever is on the right, and we'll set the arity of the token to binary and return it. We can do asterisk exactly the same way. We still have a, the only difference is it's asterisk instead of plus, and it's 70 instead of 60, but otherwise they're exactly the same. Whenever we have things that are that similar, we know there's a chance to do something smarter. So I'm going to create an infix operator, or an infix function, which I'll use to define my infix operators. So it's going to take an ID, a binding power, and an optional lead function. If we're not past a lead function, then it'll create a default lead function, which is the one which takes the thing on the left, calls expression, and takes the thing on the right. So having this infix function, I can now start defining my infix operators. And again, it's looking declarative, but it's actually functional. So this says that my plus operator is looser than my multiply operator, but tighter than my comparison operators. And by the way, all of my comparison operators are at the same level of precedence. In your favorite programming language, do they all have the same precedence? Anybody know? They probably don't. In most languages, the inequality operators, less than or greater than, don't have the same tightness as equality. Again, another opportunity for error. The ternary operator is a special infix operator because it takes an additional thing afterwards. So we specify that by passing in a function which will parse those, which looks like the others. It will take the thing on the left, get an expression to get the second thing, will then match the colon, and then get the expression for the third thing, and set the arity to ternary. In most of our languages, we'll have some things which associate left to right, but that's not confusing enough. So we'll also have things that associate right to left. So if you have a number of operators with the same precedence level, the tie gets broken by directionality. And some will go one way and some will go the other. So an example of things which go the other way are assignments. Assignments always get evaluated from right to left. We'll create an assignment function which will help us to specify those things. And we can also do some deeper checking here. So I can make sure that what's on the left of the assignment is an L value. That can be a difficult thing to determine syntactically because the L value rules are more complicated than the regular expression rules. But adding special cases in this system is really easy. So I can just do that checking here instead of trying to do it grammatically. And then once I have that, I can then go ahead and create or specify my assignment operators. I do prefixes the same way. A prefix uses a nud because there's nothing of interest on the left of a prefix. So having that, I can now specify plus, minus, and so on, my prefix operators. The parent operator for grouping is slightly special, so we pass in a function. So it will parse an expression, look for the closing brace, and then return the expression. When Pratt wrote his paper, he was thinking about expression languages. And expression languages are great, but we don't like those. They're not emotional enough. We prefer to have statement languages. We want to have statements and expressions. And his language didn't allow for statements, but it was easy to adapt the system to do that. So I came up with a first null denotation. In the statement position, you can have there are certain nuds which only make sense in that position. And so I call those things FUDs, or first null denotation. And I can have a statement function which will allow me to declare or to create the symbols that will be used for statements. It will first look to see if the token has a FUD, and if it does, it will call it. Otherwise, it will assume it's an expression statement. And then I'll look to see what kind of expression I got. In most of our languages, any expression can be a statement, which is crazy. I think the only two expressions that make sense in statement position are assignments and invocations, and anything else is likely to be an error. But since B, at least, we've allowed that, but I think we shouldn't. And then finally, it'll match a semicolon, and it's done. Very often, we'll want to have more than one statement. So statements allows us to parse a list of statements and put them in an array. And we can tell if a token is likely to be the next statement if it has a nud or a FUD. If it does, then it's probably a statement. If it doesn't, then it probably isn't. We can then parse blocks. A block starts with a curly brace and then will contain some statements and then a closing curly brace. Okay, and then we can match, we can start defining our statements. So a statement will take an ID and a FUD function, and so we'll get a symbol for that statement and assign the FUD statement to it. So here's an example of an if statement. We first skip the decorative curly brace or decorative paren. We parse the condition. We match the closing brace or closing paren. We parse a block. Then we look to see if there's an else. If there is, then we get the other consequence. And then we set the arity to statement, and then we're done. So in the box is an if statement. That is the statement that this expression or that this function is going to match. But to show you some of the flexibility we have in the scheme, suppose I want to parse or have a language which looks like BCPL, at least in its if statements. So this is the code for parsing BCPL like if statements, and in the box is an example of such an if statement, basically taking the parens off. This is sometimes called paren-free, and at various times it looks like this might make it into a future edition of ECMAScript, but so far it hasn't, mostly because public response has been so vocal. People love that paren, and it looks like we can't remove it. Or if we want to make it look like algol 68, in the box is an algol 68 if statement, and this is a code which will match that style of if statement, basically just by matching on the phi. then this is the key to the whole thing. This is the expression statement. You call this with a binding power, and that returns a tree which represents that expression. And this is the single most brilliant function I've ever seen in my whole career. In this, Pratt has taken all of the theory of parsing and all of its complexity and reduced it to a simple loop. So when we enter this, we first call the nud of the current token, and then as long as the binding power of the next token is greater than the right binding power that we passed in, we call leds. And we keep doing that until we're done. And that's it. All of the complexity of parsing is in this simplest of functions. So when we are doing stuff right, it's when we've taken a whole lot of complexity and removed it all and just come up with a simple thing. And I have never seen a better example of replacing complexity with simplicity than this. I love this. This is my most favorite function in the whole world. And all this works. So we want to take that statement and produce that tree from it. And what I showed you will do that. In fact, we could look at it as, this is the data structure that it'll produce. And we could then take that data structure and give it to a code generator, give it to an optimizer, give it to an interpreter. That an interpreter can execute this stuff directly. And this is the trace that code's going to do. And so you've seen every one of those functions, and those functions weren't doing anything very complex. There's not much code going on. So this technique is really fast because it's hardly doing anything. It's just going around comparing numbers and building trees. This is another example of a statement. This one, because of the difference in precedence, the tree is balanced in the other way. This is the data structure that represents that tree, and this is the parse that generated that one. And again, it's really simple, and it's really fast. There's hardly anything going on. So that's top-down operator precedence. It is easy to build parsers with it. It is really fast because it does almost nothing. It's, in fact, fast enough to use as an interpreter. And it's dynamic. You can build DSLs with this. In fact, you can build DSLs inside of another application because it's really lightweight. You could also build extensible languages. You could have functions in your system which add new capability to the structures that you're using to build your language as you're running the language. So you can add stuff. So one view of application development is you should first design the language which is the ideal language for writing your application, and then write your application in that language. This allows you to easily do that. We can also get rid of reserved words. Reserved words are bad for programmers because you have to remember this list, and sometimes that gets in the way of the things you're trying to express. And it's bad for language designers because if you discover later something that you needed to add to the language, very often you can't because people are already using the best word. So because this technique is so dynamic, you're not freezing all of this complexity into static data structures. It's all dynamic. You can have policies like any word can be used as a variable name. But if you use a variable name in a function, that name cannot be used for any other purpose in the function. And having such a rule means you don't need reserved words anymore. So it's good for programmers because they don't need to know or care what the reserved word list is. It doesn't exist. And it's good for the language designers because they can add new stuff to the language at any time and never have to worry about conflict. Because anyone who's already using the name is not going to be using the new feature, so who cares? Finally, I have some advice for language designers. I think we should all be designing programming languages. I think it's a great thing. It's a lot of fun. It's the nerdiest of arts, and it's something that we can all enjoy. So first, I would recommend that you try to embrace minimalism. In your language, try to have conceptual minimalism. Also, notational minimalism as much as possible, but don't get cryptic. Try to provide as much clarity and error resistance as you can. One of your primary goals should be to try to make your language confusion-free. Confusion is the source of all errors. And so if we can avoid sources of confusion in our languages, we're going to have an easier time. Try to make it readable, and I find there's a huge amount of misunderstanding as to what readable means. I think readable means that it can easily and correctly be understood by a reader. Most people understand readability to mean I like the way it looks, and that's a completely different thing. Innovate. We already have a lot of Java-like languages, so if you find yourself writing Coke bottle equals new Coke bottle, walk away from the machine. We've already been there. That ground's been really well covered. Try to find some other dimension on which to innovate. Select your features very carefully. Don't just take every feature you ever saw and try to put it into your language, even if they're all really good. Beware of the idea that something is sometimes useful. This feature is sometimes useful, so I want to put it in my language. I defy anybody to suggest anything, real or imaginary, which is not sometimes useful. Even things which are ridiculous and dangerous and nasty, those things are sometimes useful. So if that's the only criteria you have for new features, you don't have a criteria. So try to come up with better reasons for why you're including things. Avoid universality. There have been a lot of attempts at making the one universal language, the language that's good for everything. That doesn't work. What seems to work better is design a language which does one specific thing really well. And chances are there are a lot of other things it will also do really well. But at least you'll do one thing really well, and that's better than a lot of other languages can claim. Help people to manage complexity. Dealing with complexity is the most difficult thing that we do. So finding the structures, the leverage which allows us to do that is really important, and promote quality as much as possible. We want to make programs that are really good. Make new mistakes. Don't make the old mistakes again. Inevitably, you're going to have to make some old mistakes because you can't innovate on every dimension at the same time. But be really cautious as to what old mistakes you're going to propagate. For example, Ken Thompson, I think, is one of the smartest guys to have ever lived. He has pushed our art so far ahead, but I think he had terrible taste as a syntax designer. But he understood how we think, or maybe we've been so influenced by how he thinks that we cannot see the many mistakes that he put into C. And those mistakes have been propagated into virtually everything that's happened ever since. We don't have to keep doing that anymore. The thing that I like best about CoffeeScript as one of the new JavaScript variants, it's basically exactly the same language as JavaScript, except it doesn't have the B-flavored syntax. It has a different kind of syntax instead, and it's great. It used to be said that if a new language didn't look exactly like C, it had no chance of catching on. And that doesn't seem to be true anymore. We're finally breaking that after so many years. So, do that. Let the language teach you. I recommend to people learn as many languages as you can, because when you get deep in a language, it can teach you. And your language can teach you too. Embrace Unicode. So most of our languages are stuck with the ASCII set. We have the ASCII operators. Unicode is full of thousands of amazing special characters, which could be really good and effective for communicating what we want to do in our programs. We're not using those because it's believed that most programmers are not smart enough to be able to get codes onto the screen unless there's a picture of it on a button that they can push. I don't think that's true. I think we can actually puzzle that stuff out. So consider that. You certainly don't want to go crazy, and you can certainly go crazy if you start putting way too many goofy characters in. But we don't have enough bracketing characters. We've gone to using angle brackets, which was maybe a mistake, because we don't have enough other things. But there are those wonderful Japanese corner brackets, which are great, and the brackets that look like that. There's a lot of opportunity for our languages. Leap forward, of course. Don't be doing the same thing. And they're forgotten treasures. We're very good at reinventing the same basic sequential language. Our new languages are not that different from Fortran in terms of how they're organized and what they do. But there are things that we left along the way which are not well represented in our current languages, which are worth revisiting, like state machines and constraint engines, other ways of thinking about how you do things that go beyond just one thing after another. Exploit parallelism. One of the biggest challenges we have is what to do with all of the computing capability that's in front of us. We're stuck with all these sequential programming languages, but as we go more and more parallel, they become less and less effective for what we're having to do. In particular, in distributed programming, we now have clouds, and we've got lots of cores, and we don't know what to do with them. So I think that's going to be the next interesting thing for our languages to deal with, is how do we take full advantage of big parallelism. And then finally, have fun. It really is a nice hobby, and I think everybody should be doing it. And one last thing. Let's get rid of these. And don't do it the way JavaScript did. The way JavaScript did it was it left these in the grammar, but allowed you to leave them out by using an error recovery mechanism. So if it goes parsing and it gets an error, it'll take a nearby line feed, turn it into a semicolon, and then back up and try again. It's like, no, don't do that. It's pretty easy to come up with a semicolon-free grammar. Do that instead. Finally, if you want to know more about top-down operator precedence, there are two projects on GitHub, which are both freely available. The first one is a simple top-down operator precedence parser for simplified JavaScript, written in simplified JavaScript. The other is JSLint, which is complicated JavaScript trying to do just the good parts, which is bigger than simplified JavaScript. And then for more explanation as to how it works, there's a chapter in Beautiful Code which describes its operation. So that's what I have for you this morning. Thank you and good night.
So thank you very much. I know this was a pretty exciting talk. It was, I struggled to type in a question trying to follow the talk at the same time, but we nonetheless do have 3 questions that you guys put in. And given that we have very little time, I'll let Douglas choose one of the questions, maybe 2, depending on how long the answers are.
Isn't language design just a special case of API design? No, I don't think so. I think with API design, you generally have a more specific idea as to what's going to happen and how it's going to be used, whereas programming languages are a much more general, abstract tool. The challenge for programming design is with each generation we want to level up. So with Moore's law, the hardware gets to level up every 2 years or so, right? They double. We only do it every 20 years or so. So we are much slower in figuring it out, and most of that slowness is due to our own stubbornness and addiction to style. It took us a long time to decide to get rid of GOTOs because a lot of people thought GOTOs looked really good and didn't understand that GOTOs were making programming harder. And we're at a similar place today, I think, with classes and some other concepts. So classes are great. They've pushed the state of the art ahead tremendously, but have also locked us in place. And so they're preventing us from going on to the next thing, which is going to be even better. So those are issues that you don't have in API design. That's a completely different space.
Thank you.